What's up, physics nerds? Today I'm going to be talking about momentum, which is the mass of an object times its velocity, and impulse, which is the average net force exerted on an object multiplied by the time that that force is exerted. And I'm also going to talk about how that affects motion. But before I do that, I'm going to have my boy Henry explain momentum and impulse to you.
So, my friend Dylan over there already told you about linear motion, but he didn't show you the equation because he's mean like that. P stands for linear motion. Linear motion is also known as momentum. This is the equation for linear momentum, which is equal to mass multiplied by velocity. This is the symbol for impulse. Impulse takes a little bit of explaining. Acceleration is, as you know from Newton's second law, equal to the net force over mass. We also know that acceleration is just generically equal to the final velocity minus the initial velocity over the final time minus the initial time. If you take both parts of that equation, you can equate the net force over mass to the final velocity minus the initial velocity over the final time minus the initial time. From here, all you have to do is cross-multiply the equations to come up with the net force multiplied by the final time minus the initial time being equal to the mass multiplied by the final velocity minus the initial velocity. And from there, since we already know that the mass multiplied by the final velocity minus the initial velocity is equal to impulse, we can get that the net force multiplied by the final time minus the initial time is equal to the impulse. So, now these are the actual principles behind those concepts. The conservation of linear momentum basically is just stating that so long as no external force acts upon a system, the final linear momentum minus the initial linear momentum is equal to the impulse. So the change in linear momentum is equal to the impulse. And according to the impulse momentum theory, the net force is equal to the mass multiplied by acceleration, which is also equal to mass multiplied by change in velocity over change in time, which is also equal to change in linear momentum over change in time. And this is the actual point of the impulse momentum theory. The impulse is equal to the average net force multiplied by the change in time. And from there, we can get the average net force multiplied by the change in time is equal to the change in linear momentum.
Hey, you know what music would go really well with this lab?
What?
The Mario Kart Double Dash Rainbow Road.
Hey, on behalf of the Nintendo of America legal team, I do not condone the unauthorized use of this music. You must stop it at once.
Now that we hopefully have some non-copyrighted music playing, we'll test these equations in an experiment. To test the conservation of momentum, we roll two carts into each other on a low-friction track. On each side of the track is a motion detector. Both are plugged into a LabQuest tablet in order to take data. Data for this experiment must include the mass of each cart, which are equal in our experiment, and the initial and final velocities of each cart. The initial momentum of the entire system, which is the initial momentums of both carts added together, equals the final momentum of the system, which is supported by the slope of the graph being close to 1. This means that both variables, initial and final momentum, are equal to each other. Initial momentum is our independent variable here. Next up is the impulse momentum theorem. To test this one, we roll a single cart on the track into a force sensor with a single motion detector on the opposite side of the force sensor. We use the motion detector to get the initial and final velocities of the cart right before it hits the sensor and right after, which we would then use to find the change in velocity. Then we use the average force applied by the force sensor, which equals net force since other forces add to zero, and the time in which it is applied to gain the impulse. That way we can find out if impulse equals change in momentum. Again, the slope of the graph should equal 1, and it is close to doing so. For both graphs, setting the intercept to 0 on Excel will cause the accuracy of your results to excel because you expect 0, 0 to be a point on the line if they are both supposed to be equal. An easy real-world example of impulse and momentum is the bow and arrow. We'll take the arrow as our system, which has an initial momentum of 0. Then the bow applies an impulse on the arrow, which changes its final momentum, allowing the arrow to be fired. Anyways, guys, if you did learn anything useful, make sure you transfer some momentum to that subscribe button. It's right down below, and it turns out at the time of this video, 0% of our viewers are actually subscribed. So it really would help us out. Thank you so much, guys.
Nerds.
1 week later.